So today we'll begin with what's called the Simson line. Not Simpson like the cartoons, but Simson, so without the P. So the Simson line is, you construct a triangle, it's circumcircle, and we choose a point, a triangle ABC, and we choose a point P on the triangle. So on the circumcircle of triangle ABC. So we choose a point P. The Simson line, or it states that if we do,
it's a P because there's no P in the Simson.
so let's say that. Yeah, my diagram is not that accurate. It's kind of hard to draw it.
Wait, I'm confused.
How do you draw it on the light so far?
Okay, so
That's irrelevant.
okay, so let me just draw it quickly. Then I explain what I actually
Can you
did.
just like write it down in words?
Okay, so what we do is we have this point P on the circumcircle, and we draw the perpendiculars onto each of the sides. So the perpendicular to BC is the foot of the perpendicular is the point F here, and we drop a perpendicular onto AB, that's point D here, and we drop a perpendicular onto AC, and that's E here. So this theorem, or the line, or the theorem states that this is a line.
What's the line?
DEF is a straight line. So that's what things state. Yeah.
The perpendiculars can be outside. Yeah.
Yeah, they are. Like this one is, we extend AC to drop a perpendicular onto it, and yeah, the other one's just lying on the thing itself. So we'll actually prove this using basic angle chasing. So I know it does look like, how on earth do you actually do that? Because how do you prove that these three random points are lie on a straight line? But it's actually not as bad as you think. It's just a bit of angle chasing. So what we want to show is that the angle between D, E, and F is equal to 180 degrees, because that just means they lie on a straight line. That's exactly what this is equivalent to that. So what we want to show is that these three angles sum up to 180 degrees, right? So we know that this angle is 90 degrees because that's a perpendicular from P to the point BC. So all we have to show is that the sum of these two angles, so what you want to show is that angle EFP plus angle DFB is equal to 90 degrees. That's what you want to show. Everyone see that? So what you'll do is you'll construct lines PP and lines PC. Because that's nice, because you have a lot of cyclic chords to work with if you actually construct those lines. So now call angle EFP alpha. So we have that alpha. And call this beta. So call that beta. Okay, now I see it. Okay, sure. So we call that alpha and we call that beta. So we know that the chord F, D, B, P is cyclic. And we see that because that's 90 degrees and that's 90 degrees, so these two subtend 90 degrees, so they lie in a circle, right? So we know that that angle here, so angle DPB is also alpha, right? And so using triangle DPP, we get that DPP is 90 minus alpha. So DPP is 90 degrees minus alpha. And from the fact that CEPF is cyclic, because these angles add up to 180 degrees, since that's 90, so CEPF is cyclic. So that angle is equal to that angle over there, so that's beta also. So ECP is beta. So ECP. So now finally we have this one big cyclic quadrilateral, so ACPB is cyclic. So that angle, the interior angle, is equal to the opposite exterior angle. So 90 minus alpha is equal to beta. So 90 minus alpha is equal to beta from the big fact that the big quad is cyclic. And that's exactly what we wanted to prove, because if you take that to the other side, we have A plus B is 90. And therefore, that holds. And so that's 180 degrees, and therefore they actually don't lie in a straight line. So the alpha is...
No, at the bottom, the last line.
Oh no, that's the same.
It's alpha.
Yeah. Okay, cool. So we move on to something that I already mentioned earlier, but we didn't actually have time to go through. So I'll be doing Ceva and Menelaus. They often come hand in hand because they both deal with ratios, and yeah, they just come together. So I'll start with Ceva. So since we actually I did mention this earlier, does anyone remember what it says? Yeah, Amara.
When you draw 3 CDNs.
Yeah.
Yeah. And then label it.
3 Cevians, so that's a Cevian, that's a Cevian.
Three concurrent.
Oh, 3 concurrent Cevians, okay. Okay, yeah.
Then
I'll label these A, B, C, D, E, and F.
Then AF over FB
Yeah.
times BD over DC times ECE, ECC, same thing, over EA, oh yeah, equals 1.
Yeah, that's what it says. So, and yeah, if you don't remember this, I did say earlier, but if you don't remember this, it's just going around in a circle. So that over that, times that over that, times that over that is equal to 1. And to actually make this complete, we put the absolute value signs so that we don't actually use negative directions, because there's what we call negative directions. So if you just put these signs, it means the length of the line, not really which direction it goes. So we just put those there. because technically AE is equal to negative EA if you're using signed lines. So we just put these to show that it doesn't really matter about the sign. So AE is just the absolute value of AE is equal to absolute value of EA in this case. Yeah. So to prove this, we use something very simple, ratio of sides using the areas. So we'll begin with finding the ratio of BD to DC to something that we can work with and is common amongst these different ratios. So since triangle, let's call this point O. So that's not the center or circumcenter, it's just a random point O. So it's not really a center, so it's just. So triangles B, O, D, and triangle triangle C, O, D. If you consider this as the height of these two triangles, then the ratio between these two areas is just the ratio of the sides because they have the same height. So we know that BD divided by DC is equal to the ratio of the area of BOD and COD. So these lines for triangles means the area of that triangle. So if you have a triangle and those two lines at the end, that's just the area. So we have that, and we do it for the bigger triangle as well. So if we have this big triangle ADB and ADC, we do the same thing. We consider a common height here, and so the ratio of these two triangles is just this length over this length. So BD, once again BD divided by DC is equal to the area of triangle ABD divided by the area of the triangle of CBD. CDA. Yeah. So now there's a bit of algebra that we're going to use here. So we're going to claim that BD over DC is equal to triangle BOD minus the area of triangle ABD divided by that minus that. So COD minus, should probably swap this around because the other one is bigger. So ABD minus BOD, and this one would be CDA minus COD. So this is what we're claiming. So we know that that's definitely true. That's definitely true. So we claim that these two imply that this is true. So I'll see we have to prove this, which is not really a geometric thing, it's an algebraic thing. So in other words, what we're trying to prove is that if we have two real numbers A over B is equal to C over D is equal to some ratio, constant ratio R, we're trying to prove that A minus C divided by B minus D is also equal to R. That's what we're trying to do. Okay, so if this was true, A minus C over B minus D is equal to R, that would imply that, so we use these two double-sided arrows to show that this is true if and only if this is true. Yeah.
Is that one, you know, you say DC is, that BD over DC is equal to ABD, that thing?
Okay.
Yeah, what are those three letters to the right?
CDA.
No, the bottom left, yeah, those.
CDA.
Okay.
Is that clearer? So if this was true, so I was explaining that this means if and only if. So meaning if that's true, that's also true. So they imply each other. So then A minus C would be equal to R times B minus D. Right? And that would imply that A minus C is equal to RB minus RD. And here, what you do is we'll divide by B, since B is non-zero, because B is the denominator of that, so it's non-zero. So we divide by B. So that would imply that A over B minus C over B is equal to R minus RD over B. And A over B is just R. So that means that. And C over B is just C over B. And that will be equal to R minus RD over B. So we do that as that and that as that. So therefore, that just can just cancel these two. And this means that CB is equal to RD divided by B. So we can just cancel this B and take this D to the other side, so that to the bottom of the other side. So that will imply that C over D is also equal to R, which is true since that's the definition of R. So that actually holds. So we can not assume, but we can actually write DC as the area of that minus that divided by the area of that minus that. So cool. So now we have that, and we'll carry on. Yeah. So now the area of ABD minus the area of BOD. So if you have ABD and you minus BOD, this small one, so it's just this remaining. So it's just AOB remaining. So BD. So it's AOB. And similarly, if you subtract this from the small one, you get AOC. So that's what BD over CD is. And if you do that for all these sides, so we did it for BD and CD, if you do it for AF and FB, exactly the same process, you get that AF over FB is equal to the area of triangle AOC, because that's the one that corresponds to this one, and the other one will be C. And if you do it for the third side, AE and CE, you get that. CE over AE. So get that, that's that. And if you multiply all these ratios, so if you multiply this by this by this, that would cancel with that would cancel with that, and this would cancel with that. Therefore, the product is 1. So if you multiply that, you get that A BD over which is what you wanted to prove. So yeah, that's what Ceva's theorem states. And the converse is also true. So if you have Cevians such that this holds, and such that the product of these ratios is 1, then the Cevians are concurrent. It's not hard to prove that, because you say if these say these two intersect, and that there's a point such that that's f prime, you can show that af prime divided by f prime b is equal to af over fb. And since that cuts, this line cuts this this point cuts this line in this specific ratio, then there can only be one point that actually does that. So that's how you show that then f is equal to f prime. So yeah. Now move on to similar thing. Yeah. So move on to Menelaus theorem. So Menelaus theorem is also quite similar. So we begin with drawing a triangle. So this kind of
two triangles.
yeah, so it's just an extension. I'll just define what they are, just real quickly. Sure. So we have a triangle ABC, and we consider point E on the side AC, and we draw in a line such that it cuts BC at D and intersects the line AB at F. So that's a straight line, and that's a straight line. So I want to show that this ratio holds.
Isn't that not AF the first one? Is it AB?
No, it's AF.
So then how come the one CE EA
CE?
over EA?
Just like we're saying.
Must be C. E over C.
No, it's just they times together to get one. Doesn't matter.
Okay, sure. So how we do this is,
Sorry, shouldn't the first one be AB over BA? Because all the others, you can tell the midpoint and then, not the midpoint, but the points between the two.
No, in this case it's not, because this is not Ceva, so we're not taking the. So yeah, so
You might explain why, because it's kind of like the negative distance.
Okay.
So if we're in between, we need to just go to F have to be.
yeah. But anyway, we are going to prove that this actually holds, because this is really independent of Ceva. It's not, doesn't follow from Ceva, so it's not really that we're using Ceva. So yeah.
What's the theorem where the ratio?
Oh no, as you can see here, I actually took the absolute values. So
without them, it would just be -1.
yeah, so without that, well, I'm not sure if I put my lines as directed in this case, but it is -1 if you use directed lines. So okay, maybe I can discuss that later, but it's not really necessary because you don't use directed lines often. So we construct perpendiculars to the line DEF. So we construct perpendiculars from B, from C, and from A. So we extend this one, right? And we assign, we let this one equal A, this one equal B, and this one equal C, right? So now what we can do here is quite a few similar triangles. So we can see that, we can call this point X, this point Y, and this point Z. So you can see that triangle XDB is similar to triangle no, Y, that's Y. Triangle YC, YDC. And here we have that triangle CYE. AYZ. It's not hard to see that. That's because that's parallel to that, because they both intersect this line at 90 degrees. So therefore, that angle is equal to that angle, and that angle is common. Or just that angle is common. That's 90 degrees. It just follows that all the angles are equal. And same thing with this one. So that's that. And so now we try to find these ratios in terms of the lines A, B, and see what follows from there. So AF divided by FB is equal to AF divided by FB is equal to A. Oh no, I forgot to mention one other similar triangle. Two other similar triangles. So triangle FBX is similar to triangle FAX as well. FAZ. So because those two are parallel, so that means that's equal to that, and that's 90, and that's 90, and that's common. So yeah.
On the second line where you wrote this in the triangles, shouldn't it be triangle AYE? For CYE is similar to AYZ.
So CYE, right? CYE is similar to triangle AYZ. Yes, that's
AZ. Yeah.
Oh yes, yes.
E is the
Is the point.
E is this point.
Yes.
So why should we AZ?
IEZ instead of IYZ.
I think you mistook that point for the other point.
Oh, sorry. Yeah.
Yeah.
Yeah. Sorry. And that also is true because those two lines are parallel, and that's that angle is common. So AF over SB is equal to A over B. Because A over B is just that over that, which is equal to AZ divided by XB. And that's true because of that similarity at the end. And BD divided by CD. Well, this is not directed, so it's just the length, so not the directed length, is equal to D is equal to B over C because of the first similarity there, and CE divided by EA is equal to C over A because C over A because of this one here. So now, if you multiply all these ratios, this A cancels with this A, this B with this, and C with this. So then this then follows from there. So that gives you that. So that's what's called Menelaus theorem. It could be stated differently. It could be that if this ratio holds, then that means these three lines lie on a collinear or lie on a straight line. So there's different variations of saying it, so, but they're all equivalent to this statement. Now move on to so now I'll move on to the 9-point circle. So the 9-point circle is a circle with 9 points, basically. But those points are of course very specific. So it's not just any 9 points, because if you have a circle with 9 points, there's nothing really special about that. So that's supposed to be a circle.
That looks like a Dorito.
That's a bit better, but I still don't like it. Okay, that looks better, right? So, has anyone actually ever seen the 9-point circle or know what these points are? Oh, it's in here. So, okay. So the 9-point circle, these points are not just any random points. So as you can see, that these are the feet of the altitude from each of the vertices of the triangle. These points are the midpoints of each of the sides, and the last 3 points, that, and that, are the midpoint of the line from A. This one, say, call this A, and call that H. So it's the midpoint of the line AH. So the 9-point circle says that all these points lie on a specific circle. And as you know from now, we're not just going to be like, oh yeah, that's true, and just move on. We're actually going to try to prove that these points actually lie on the circle. So we'll first label it to make it clearer. So we'll call the triangle ABC. Call the midpoint M, N. No, wait. Okay. Call this midpoint L. Call this M, and call this one N. And call the feet of the altitude D, E, and F. X. Can all of you guys see this color? The red?
Yeah.
Okay, now just use the blue then, I guess. So, we're going to show that Y, Z, MN is a rectangle. So we want to show that show that that's a rectangle. Any ideas on how to do that? How do you usually prove that something is a rectangle? So what are some of the ways to prove that something is a rectangle?
Prove the 90-degree angles.
Okay, so we have to show that one of the angles is 90 degrees, right? And
yeah.
If we have that and we have that, it's a parallelogram, therefore it's a rectangle because it's parallel. So that would be parallel to that. And if one of them is 90, then that has to be 90. So that would be a rectangle. So that's what you're going to do. So parallel lines, we're going to show that MN is parallel to YZ, and AY is parallel and MZ is parallel to NY. So that's what you're going to show now. So now by the since N is the midpoint of AB and M is the midpoint of AC, it follows that NM is parallel to BD by the midpoint theorem. So AN is parallel to BD. And also YZ. Oh, and also since Y is the midpoint of HB and Z is the midpoint of HC, it follows that equal to that equal to that. So YZ is also parallel to BC. So YZ is parallel to BC. So since that's parallel to that and that's parallel to that, so all three are parallel. So we know that AN is parallel to YZ. NM, MN, not AN, is parallel to YZ. And by the same logic, using the fact that NY is parallel to AD, since that's the midpoint of that and that's the midpoint of that, and MZ is also parallel to AD, we get that so now we have that this figure here, NMXZ, is actually a parallelogram. So all you have to do now is show that one of the angles is 90 degrees. And that follows because this angle here is 90 degrees because that's parallel to that. And since that's also parallel to that, that's 90 degrees here. So that's actually a rectangle, not just any parallelogram. So NMZF is as a rectangle.
It's a rectangle because
Parallelogram.
It's a parallelogram, and that's 90
how can you know
because YZ is parallel to BC, and so that's also parallel to that. So that's perpendicular to that. So that's also 90 degrees. Question? Okay. And similarly, we can show that. When I say similarly, I mean do this all over again. So there's really no need for us to like actually do it. It's literally the same thing. We can show that in we can similarly, I know it doesn't look like that on the sketch, but you can also show that N, E, Z, what is this point? L. So that's also a rectangle, right? Yeah.
Shouldn't it be NX LE?
No, I don't think so. Yeah. But yes, it should. Sorry. Okay, yeah. It looks messy now, so I can actually see. Okay, so that's in X. ZL is a rectangle as well. Therefore, and actually, NZ is the diameter of the circle through NX, Z, and L because that's 90 degrees. Yeah.
How do you know where to put the middle of the compass when you draw the circle? Like, do you know if there's a point?
What do you mean by middle of the?
You want the center of the circle.
Like, is there a way to find out the middle of the circle?
Of the circle? It's just the intersection of, well, so if once you find out that, so you know that the diameter, DL is a diameter because that's 90 degrees, and you know that there's several 90 degrees also, so you know that FZ is also the diameter of the circle. Therefore, it lies between the intersection of, so if you have two diameters, so if you have, that's a diameter, and you have, that's also diameter, so that will be the center. So if you were to draw it, you draw this line in, that line in, and they both diameters were in the same. That's the center. So that's how you want to draw it. Also for this one, since NZ NZ subtends a 90-degree angle. So here also NZ is the diameter of NMZF. So that's also true, right? So therefore, these 6 points here, N, X, Z, L, and M and F lie on a circle with that diameter. Can everyone still see why that's true? Well, it doesn't look very clear on the diagram, but since that's a circle with diameter, then all those points actually lie on that circle with this diameter. And now the only points you have to prove that actually lie on this circle are points E and points D, because points E and points D.
Sorry, I just want to know, is that correct? N, M, Z, F is a rectangle. Should it be N, N, Z, Y? One up. The line one up as well?
Okay, sure. So what you want to show is that E, D, and F are also on this circle. So now, it's clear right here.
Don't you just prove that by converse of tan from the same point?
Yeah, I just can't see properly what I've done here. Okay, so well, it also follows that why did I write that? Oh, because these are also diameters, since that's 90 degrees and this lies there. So therefore, E is E on the circle already.
It's not really a diameter.
NZ, so sorry. NZ is equal to MY, right? Yeah, MZ is equal to. Oh my God.
In Z and Y to diagonals of the
Okay.
No, it's that other dotted line.
Yeah, so since that, oh my God, this is so horrible. Since
It's not along that line. So it's the middle of the circle is where NZ and MY cross.
it is the middle of the circle. So yeah, that's actually right. So where MY and NZ cross, that's the middle of the circle. But then, since that's the middle of the circle, then that means that that's equal to that. But then, since that's a rectangle, the diagonals bisect each other. So HX is equal to LY. So LX is also diameter of that circle. So therefore, we have that equal to that equal to that. Similarly, we can find the other one, MY. MY is just equal to NZ. So that's true. Therefore, all of this, and then we can show that since since MY subtends the angle E at 90 degrees, so that point also lies on the circle with diameter MY. Therefore, E also lies on that circle. Similarly, D also lies on that circle, and F lies on that circle. So all of these 9 points lie on that circle. So that's the 9-point circle. And try to find what happens when we have special cases. When, say, for example, triangle.
Obtuse triangle.
No, not when it's obtuse. When we have triangle ABC is equilateral, then how many points are actually on that circle? Is it more than 9? Is it less than 9?
6.
So yeah, 6. So that point would coincide with that. So that would be exactly the same thing, and that would be exactly the same thing, and N and F would be the same thing. So if it's equilateral, that's a 6-point circle.
And wouldn't the right angle triangle have 7?
A what?
Or 8? I don't know, a right angle triangle.
No, right angle triangle will still have 9 points because right angle triangle will have 7 because one of the obtuse angles will be equal to. Yeah. Wait, is that true?
Obtuse
Yes.
because they will both meet at the corner. They'll both like be on the
Still
corner.
exists. That will still exist. No, it will still be 9 points if it's right angle triangle because none of these points coincide. Unless you can tell me which points would be the same point, then I still think it would be 9.
No, I'm saying so. Let's say ADC was the right angle triangle.
Mm-hmm.
So
Okay, let's say we have. Let me just draw a smaller diagram here, right? So we'd have this midpoint here, and this midpoint here, right?
Yeah. So you'll drop the top of top two perpendicular down to the corner.
So that's equal to that.
Now I'm not worried about the middle now. So now you have the drop perpendicular in that corner at the bottom left.
So that.
And then you also have another drop from the other side. No, it must be straight. Yeah, so
Wait, let's draw this properly. So we have this.
yes.
So let's just connect this to our diagram. So let's say that's A, and that's B, and that's C. And then N would still be here, right? And
It
L
doesn't matter about the N and the L.
and M would still be here, because that's equal to that, and that's equal to that, and that's equal to that.
Yeah, so when you drop A down to BC, it will.
Yeah, so D, that would also be D.
And it will be.
And will be-
C dropping down to AB.
Yeah, so that would also be F. And that would be L. And that guessing would be E. So how many points are here? 1,
I think altogether it's 8.
3, 4. It's only 4 points, not
What?
because that point.
No, what about the intersecting lines? You still have to put the middles of those others.
Which lines?
Those ones? The Covian draws. The Cevians, the middle of the one side of the Cevian.
The X1, Z point, the Euler point.
Oh, yeah.
Okay, can I come draw it?
No. Oh yeah, I see. Okay, yeah, 7. Okay, sure.
So the Cevian.
The line that goes through the also center, circumcenter, incenter, and
Oh yeah, it turns out that this circle is actually tangent to the X circles from. So if you draw the X circles, let me draw this one here. So if you draw one of them here, it turns out that this circle will be tangent to that, and that's called Feuerbach's theorem. So German person, German mathematician. mean, this is the proof. This is also quite long, and I think I've run out of time, so I can't do that now. So yeah, so that's pretty much it. And yeah, that's the end of the lecture. Thank you.